in the last lecture, we talked about searching, and we spent a lot of time talking about linear search and binary search because those two algorithms deserve their day in the limelight, even though we sort of take them for granted usually. And I want to do the same thing in this lecture for arrays and linked lists. Now, I'm assuming that you came into this course already knowing about arrays and linked lists, even with some level of theoretical detail, so even having some idea about running times associated. But I do sort of want to talk about them, want to give them a bit of attention, and it also gives us a chance to sort of lay down some assumptions that we tend to make about arrays and linked lists. And so these are sequence types. And I also actually want to use the opportunity to talk about this idea of a data structure. So a data structure is an organized collection of data with associated operations. And the reason why we really need to think about these things when we study algorithms is that they actually provide us a way of sort of freezing an algorithm in time, in some sense. We often use data structures as a way of splitting the various pieces of a larger task into separate computational units so we can do them over time as opposed to all at once. And so, although we haven't covered things like binary search trees yet, if you've seen those before, you can think of a binary search tree as being a way of sort of freezing the operation of sorting something in time so that you can sort it gradually. You can add elements and remove elements over time. So a data structure, in a lot of senses, a data structure is sort of a way of taking a larger algorithmic task, like sorting something or putting things in a particular order or performing a certain sequence of things, freezing it in time so that you can perform those operations gradually and you can modify the contents of the structure. And so we think of a data structure as, in a sense, being a related collection of algorithms where they can share some set of persistent data. We often use the term abstract data type to refer to the concept of a data structure for a specific task versus a particular implementation of algorithms for a data structure. And a classic example of those, of data structures, would be stacks and queues. So this course is designed to assume that you already know what these things are, so I will assume that as well. But recall that a stack is a type of collection type. It's a type of sequence where we sort of model it as if it was an actual stack of things. And that means we can put stuff on the top of our stack, and we can remove stuff from the top of the stack, but formally, we are not allowed to go in and take a look at the things at the bottom until we removed everything on top of them. And so the three fundamental operations of a stack are push, which means add something to the top, pop, which means remove the thing from the top and return it, and then peek, which means take a look at the thing on the top, but then do not return it. And there are all sorts of clever exercises we can come up with that, for example, show how to implement this function using the other two. Notice that although we probably use an array or a linked list to implement a stack, the stack abstract data type, the description of the operations needed, doesn't assume that you're using any particular type of data structure underneath. And in a sense, this is sort of analogous to the concept of like an abstract class or an interface. Somebody who uses a stack doesn't really care about how the stack works internally. We almost think about this as being an algorithmic or formal way of thinking about encapsulation. If I mention a stack, of course, I should talk about a queue. So a queue is a collection type that I like to think of as sort of the dual of a stack. Whereas a stack has this last in, first out order, in other words, you put something on the stack and you can only remove the thing you added most recently, so the last thing in is the first thing out, a queue has a first in, first out order. And we typically think of a queue as resembling sort of like a line of people or something. Whoever gets in line first, they are the first person to reach the front of the line. And so the enqueue operation puts something at the back of the line. The dequeue operation removes the thing at the front of the line. And then the front operation just gives us back the thing at the front without deleting it. And so this is a first in, first out order. The first thing to enter the line is the first thing to reach the front of the line. As I said, I think of stacks and queues as duals. They are, in a sense, two sides of a coin. They are the same basic data structure, but with one twist, the twist being the order in which elements are added and removed. The reason I keep saying that I think that they are duals, is that we are going to see later in this course that when there are algorithms that insist upon using a stack, a question we should always find ourselves asking is, hey, what happens if I use a queue instead? And vice versa. A lot of times when you see an algorithm that uses a stack, there is another algorithm that does something similar, in some cases something eerily similar, using a queue. And so we should always ask that question. If the algorithm needs a stack, what happens if we use a queue instead? And so the idea here is that Like when we specify a problem formally, so here's our contains duplicate specification again. I think this might be the last time we see it. Like when we specify an algorithm problem formally, the statement of operations needed for a data structure or an abstract data type is meant to admit the possibility of there being many options for implementation. There are lots of ways I could choose to realize the operations of a stack, and depending on which choices I make, I might end up having different running times. So there could be versions of a stack where the push operation is linear time and the pop operation is constant time. Or vice versa, where the push operation is constant and the pop operation is linear. Although, spoiler, for the specific case of a stack or a queue, we can make all of those things constant. And as I said a minute ago, like the case of like an abstract class or an interface in your favorite object-oriented language, abstract data types are sort of a way of separating out the operations somebody might need in some other algorithm from the way that they might be implemented underneath. So there are lots of ways of implementing a stack, but if you're implementing an algorithm that uses a stack, maybe you don't care about details like that. You might care about running time assumptions, but you don't care too much about how the stack is stored internally. So let's talk about arrays and linked lists. And I believe all of this should be review. So this is all here for completeness sake, and you may well be able to skip this entire lecture and just skim over the slides. You may not actually need the prose, you may not need to listen to me talk in this case. But if for some reason there are any gaps in your background, this might be helpful. So an array is a data structure that stores a sequence of elements in a contiguous block of memory. So although we in this course work in this very abstract domain, we don't talk too much about computer memory or whatever, we do need to make certain assumptions about how data is laid out because they can have impacts on the running time of things. And the assumption we make when we use the word array, the assumption that we make is that elements are contiguous. And in particular, that means that I can't just jam some new element into the middle of an array because there's no space there. 10 is right next to 187, so if I want to add something to an array, I have to make space. And one benefit of that is because the elements are contiguous, arrays support constant time indexing. So if you tell me to give you the value at index 4, that can be done in constant time in our random access model. Even if the array is massive, computing where an element is in an array by index can be done in constant time because it's done with arithmetic. I mean, in general, if I want index 4 of an array, and this is where I'll talk about the computer's memory briefly, what I do is I take the address of the beginning of the array and I add 4 to it, or 4 multiplied by the size of the elements. So I can find a particular element in an array by index in constant time. And then once I have the address, I just go there and grab it. And because memory in our model is something we can access with a constant amount of time, that means I don't have to iterate through the entire array just to find the element at a particular index. I would argue that this aspect, the ability to index an array quickly, is basically its distinguishing characteristic. All the other operations that we find ourselves doing with sequences are possible on arrays. Some of them are harder than others, but certainly arrays are the unique data structure of this type, a sequence type, that allows us to index in constant time. It actually also turns out to be true that for reasons that are not relevant as much to an algorithms course, but are worth keeping in mind, so just life advice, arrays tend to be very fast. When you implement arrays on most architectures, they tend to be very fast because the operations that you tend to perform on arrays can be done very quickly because arrays are all next to each other in memory, and we don't need to do very much overhead to go between different elements of an array. Now, because the elements of an array are stored in a single monolithic block of memory, any manipulation that modifies the order of elements in a sequence could require rearranging it, especially modifications that would, for example, remove something from the sequence or add a new element, splice a new element in. So we'll take a look at that. Let's say that we want to insert the value 17 at index 2 of the array above. When I use the word insert here, what I mean is that I would like the sequence that I end up with to be the sequence 6, 10, 17, 187, -1, -5, 225, 226. So in other words, I want to add this new element without removing any existing elements, and the only modification I want made to the sequence as a whole is I want this value spliced in. So notice that this particular array, I've left some empty elements at the end, because maybe I foresaw that I might need to insert some stuff after the fact. So because the index I want to insert at, index 17, is already occupied, the only way to get the element in there is to move stuff around. So what I could do is I could take everything after index 2, at or after index 2, and I could move all of them over by one position to the right. And if I do that, that makes a gap, and then I can fill that gap with the new element 17. Doing this, though, could require big theta of n operations. So if I chose in a really long array, if I decided that I want to splice something in, I don't know, at about index 2, then I have to move, potentially, so maybe n minus 2 items, which is big theta of n. I have to perform n minus 2, big theta of n operations just to move those n minus 2 elements. Now, once I've done that, I just add the element 17 to the space that was freed. Now, so in the symmetric case, suppose I want to delete something. Okay, so if I want to remove the element at index 4, assuming I have index 4, you tell me to remove from index 4, and typically array operations are phrased in terms of the index you're operating at. Although, if you wanted to remove a value and you didn't tell me the index it was at, I could always use, let's say, linear search to go find it. So suppose I want to remove the thing at index 4. Okay, I do that, but now there's a gap in the sequence. And in general, you can make an argument that amounts to, well, why not just let there be a gap in the sequence? Yeah, there are probably applications where you get away with that. The problem is, if I keep deleting things, eventually there are so many gaps in the sequence that I'm using up a huge amount of memory for a small number of values. And that means the memory consumption for my n values could be far greater than n. That's one problem. Another problem is, if I want to iterate over the array, if the array only has 2 things in it, and I have to iterate over 7 things to see both of them, the running time of iteration is now much larger in terms of the number of actual values in. So reasonably, we should assume that if we delete things or if we insert things, we want to make sure that when we're done, we have a contiguous block of elements. And I will go forward in this course assuming that that is the case, that we can't just leave gaps in the array. I am actually realizing now that, I don't know, about maybe 10 lectures from now, there is a time when I will gratuitously decide that we leave gaps in arrays. Don't worry, you'll see it. You'll know why I'm doing it when we get there. But in general, I will assume otherwise that we don't leave gaps. So I delete an element from an array. I have this gap in the array. I now have to fill that gap back in. So what I do is I pick up every element and I just move it back over one position to the left. And again, that could take big theta of n operations in the worst case. So in the case where I have arrays where I've guaranteed that there's always extra space available, then if I want to insert or remove at the end or within a constant distance from the end, so if I'm removing element, like n minus 1 or n minus 2 from the end of the array, then all I would have to do is shuffle over a constant number of things. In that case, the removal or the insertion is constant time. However, the worst case for insertion and removal is the case for this example where the thing we're inserting or removing is at the beginning, where we have to shuffle everything along. Now, if you know that you're going to be doing a lot of insertions and removals specifically at the beginning and end, what you could do is you could arrange it so that the empty space is on both sides. So your array itself is actually basically in the middle here. And that way, if you want to insert at the beginning, you don't have to move anything around. And if you want to insert at the end, you don't have to move anything around. And even better, you could actually assume that the empty space wraps around. So in other words, the first space you fill if you want to insert at the beginning of this is you fill this space, then you fill this space, then you fill this space, then you fill this space, and then you wrap back around here, and you just call this the new beginning of the array. So you could do that. You can arrange it so that insertions and removals at the beginning and end of the array can be done in constant time. The problem is, no matter how you break it down, there will always be somewhere in the array where if you remove something, so in this array here, my diagram is increasingly cluttered. Let's try that again. In this array here, if I want to remove from the very middle, and there are elements on both sides, well, then I might have to move those elements around. And so although there are all sorts of clever tricks for avoiding shuffling elements in certain cases, again, we're working with this best case, worst case situation. There's always going to be this worst case where you have an element in the worst possible position that requires moving a lot of other things around to restructure the sequence. However, that all said, it is true that a lot of our uses of sequence types where we have to modify the sequence do just amount to inserting and removing at the end. I mean, a lot of our uses of sequences don't even remove anything. They just insert stuff. They just build a sequence up from left to right. And so in an array, as long as you can make sure you always have empty space at the end of the array, in an array, inserting at the end of an array that has empty space available, that's constant time. And for what it's worth, that's really fast. When you have the empty space, all you're doing is sticking an element, so let's do -1. I just stick an element in there. That's just a very small number of operations, and they tend to be operations that are easy to execute. In some cases, and what I mean is for some of the algorithms that we consider in this course, it is reasonable to assume that if we need an array for some purpose in the middle of our algorithm or something, that it will have extra space available. And the cases I'm thinking of when I say that are, there are lots of cases where we're working with a data set of some kind, let's say a data set of size n, and at some point while processing it, we have to use a sequence to store some elements. But we know that we only ever have n values. So if I need to use a sequence to store some combination of my values, if I make the sequence have size n, then there's no way that I'll end up needing any more than n spaces. And so I can arrange it. If I know in advance the maximum number of things I'll need to store in my array, I can arrange it so that the array always has enough space to store whatever I'm going to put into it. But of course, in general, if I just have an array and I want to keep adding values to it, we could end up in a situation where there is no empty space left because the amount of empty space has to be scheduled in advance because the array is a single contiguous block and I have to decide how big the array is when I create it. So that leads us to this situation. Suppose I want to insert the value 445 between the 6 and the 10. The problem with this array is that there is no empty space available. So what do? Well, I guess I can insert if I can find my way into expanding this array somehow, but okay, that's easier said than done. What does it mean to expand an array? One of the reasons I added this lecture to the sequence, we all know about arrays and linked lists. Well, not all of us necessarily, but some of us might need review, but we all understand what the word array means. One reason is because there are a couple of special cases that arise, and it's good to have it somewhere down in writing how to address those special cases, and this is one of them. What does it mean to expand an array? Well, I would argue that it means this. So suppose I had an array of size 6, and I decide that I need to have more empty space at the end of it. Well, the array is full, so what I'll have to do is, I don't know, maybe I could create a new array of size 10, and then I just copy all of my elements into it. And of course, because I have to copy all of the elements into it, that's going to require a bunch of time for the copy, as well as whatever amount of time it takes to make the new array. In our random access model, we generally operate on the principle that allocating an array of size n prime requires n prime time. So I actually have to use time to allocate and initialize my array. I know, especially if you're C people, so if you're a C programmer, you're looking at this and you're a bit skeptical because you're thinking, wait a minute, I can allocate arrays in constant time because all I'm asking for is to reserve the memory. I'm not talking about initializing them, initializing each of the elements. And I agree. However, I would say if you tried to employ that insight in an actual algorithm analysis case, what you'd realize is even if it's free to make some massive array, if you actually make the massive array, you must need it for something. And if you need it for something, you're going to eventually use it, which means that at the end of the day, if you make an array of a particular size, let's call this one size p, then it will take, at some point in the operation of your algorithm, it will take big theta of p time to use the array. So ultimately, whether the time is consumed when you allocate the array versus when you initialize the array versus when you first use the array, if you ever need the array, you are going to use all of its elements. Moreover, if your algorithm allocates a massive array that it doesn't need, you could always modify the algorithm to allocate a smaller array. So it makes sense, therefore, to assume if the algorithm allocates an array, it needs the elements of the array, and therefore that it needs an amount of time proportional to the size of the array. That's one thing. Second, and more practically, if I have an array that contains 6, or in this case 7 elements, and I want to resize it, and resizing requires making a new array and then copying everything in, well, certainly that's going to take 7 operations. Certainly copying everything from one array into another requires an amount of time proportional to the number of elements in the array that I started with. So certainly, at minimum, it takes big theta of n time to go from an array of size n to an array of size n prime. Although I will treat it as taking big theta of n prime time. But even that, you might be a little bit skeptical, especially if you know a lot about the memory of the computer, or again, if you're a C programmer because and have taken a computer architecture course or something. Because you could make the following argument. Here is your computer's huge memory, and somewhere in that memory, there is your array, and you would like to resize that array. So wait, what's stopping you from just, taking out the wall here and just declaring suddenly that your array is now bigger, so building an annex on your array? isn't it true that that doesn't require any more time than it takes to build the annex? So in other words, adding one extra element to the end of an array of size 1 billion, isn't it enough to just, build on the annex of one element and be done with it? That's interesting. That sounds like an optimization, and I love optimization. So certainly if I could do that, I would. The problem is, if we talk about worst case analysis, that is not generally possible. If it is possible, you better do it. But the problem is, it isn't always possible, and we can't assume that it will be in any particular case. And here's why. Suppose your array is sitting in memory minding its business. And when you allocated your array, you only needed up to this point in memory. So it makes perfect sense that somebody else, the compiler, the operating system, the runtime environment, could easily have given you a neighbor. Maybe there's somebody else using the property right next door. And that means you aren't allowed just to knock out a wall and expand your array. That's not how that works. So if you're lucky, maybe there's memory available to resize the array without moving anything. But you can't assume that you're going to be lucky. Worst case analysis is assuming that you are the least lucky as you could possibly be. So the issue with array resizing is, in worst case analysis, if we have to expand an array, we need to assume that the only way of doing it is going down and making a brand new array elsewhere where there is a bunch of available space and then copying everything in. I say that because every time I teach algorithms, this thing comes up somehow. Somebody wants to argue that that's... the problem is I'm on their side. I actually like the idea of expanding arrays in memory. We just can't assume it's always possible. So if you're a C person, you might be thinking about the realloc function. And the realloc function is a standard library function that... well, it's up to the implementer of the library to decide how they do this, but it reserves the right, if you ask it to expand an existing array, to expand it simply by knocking down the wall and adding an annex, as opposed to moving it around in memory. However, we have to assume that the worst case happens, and the worst case is copying the elements of the array. Anyway, whatever. After we expand the array, we have empty space at the end. We can then move all the elements over in big theta of n time in the worst case to make space for the new element that we want to add. And so, of course, even if there were some magical way of expanding the array without copying elements, shifting the elements would still require big theta of n time. So at the end of the day, the accounting still works out to require big theta of n operations for an array expansion. Okay, so that's the story on arrays. I want to talk a bit now about linked lists. So in a sense, I would argue, and I do make this argument when I teach programming, that a linked list is sort of the opposite of an array. Because an array, the defining characteristic of an array is that it is a bunch of elements in a contiguous block of storage. And that makes it very well suited to applications like finding an element by index, because you know exactly where each element of the array will be by index because they're all next to each other. They're at a fixed distance from each other. It also means arrays are not very well suited to applications where you manipulate the structure of the sequence because you have to shuffle a lot of different elements to make local modifications. So back in this example here, when I want to splice an element in between indices 0 and 1, which is a local modification to the structure of the sequence, I have to move everything else in the sequence around to make a global modification to accommodate my local change. On the other hand, a linked list, which I'll now define it, is a data structure that stores a sequence of elements with a collection of these things, which I'm going to call nodes. A linked list is the exact opposite of an array in the sense of being not contiguous. The elements are they are all independent of each other. They sort of are autonomous. The structure of the sequence is dictated by pointers or references between nodes. So a node would be a combination of the element in the node and pointers to attach that node to the rest of the sequence. And that means that if I want to modify the structure of the sequence, I don't have to make global changes. I can just rewire a local area of the list. Some details that are irrelevant to us in this algorithms course, but that I have to mention at some point so that I can never mention them again. If you go to implement a linked list, you might implement a singly linked list where each element is attached to the thing after it. Or you might implement a doubly linked list where each node is attached to both the thing after it and the thing before it. And you can see that if you happen to have a singly linked list on your hands, you can travel forwards, but if you're sitting in a particular location, you can't travel backwards. There are reasons why this is helpful, and actually there are cases later in the course where if they were presented in a non-algorithms course, in a programming course, things like binary trees, we often can think of those as generalizing singly linked lists in certain cases, which actually is sort of helpful. But it is true that if you're implementing linked lists for a purpose of implementing an algorithm, you might need either a singly or doubly linked list, or one might suit the purpose better than another, depending on what you're using it for. For our purposes, what I will observe is that the overhead involved in having a doubly linked list versus a singly linked list is all constant time. So if I want to insert into a doubly linked list, it takes about twice as long as it does into a singly linked list because I have twice as many pointers to wrangle. That's pretty much it. And we know that twice as long is a constant, and therefore that asymptotically that makes no difference. And which means that for our analysis in this course, it really doesn't make much of a difference if your lists are singly linked or doubly linked. And so we pretty much ignore the topic. We just assume that if you need a linked list, you will choose whichever one serves the purpose of your algorithm best. I will add, because I do implement algorithms all the time as well, that if you can get away with a singly linked list, if you don't need the structure of a doubly linked list, well then of course you should use a singly linked list because there's less stuff to worry about and that means less overhead. And of course a constant time speed up is still a speed up. So there you have it. And that means that in this course, what I will often do is I actually sometimes draw lists as if they're singly linked, even if it sort of seems like they ought to be doubly linked, but I'm trying to remember to ensure that they get drawn like this. I'll draw a doubly linked list with this double-ended arrow, although implementation-wise, of course, there's no such thing as a double-ended pointer. There's just two pointers, one in each direction, but I'll draw it in this compact representation. Typically, when you store a doubly linked list, you keep two pointers, one to the beginning and one to the end. And for historical reasons, these are typically called head and tail. What's weird about this is that the terms head and tail come out of I shouldn't say old. Head and tail come from functional languages like the Lisp family and its descendants, and that the word tail traditionally didn't actually mean the last element of the list. It meant every element after the head element of the list. So the term tail, as one typically finds themselves using it in like a first-year programming course with C or Java now, tail is often used for the last element. That's actually sort of an anachronism. Okay, whatever. We're not here to litigate that. Come to the office hours and we can talk about weird historical trivia. So typically when we work with linked lists, we run under the assumption that the elements of a linked list are only accessible by starting at the beginning or end and working inwards. Unless, of course, you happen to be holding a pointer to a specific element. So specifically, this means that you can't just get an element of the list by index. You can't just say, okay, so this -1 is index 3. Just give me index 3. Getting the element in index 3 is possible, but the only way to get there is by iterating through the sequence, which means indexing a linked list is actually big theta of n on a list of n elements. So getting the element in the middle of the list would take n over 2 operations, because you have to go through n over 2 pointers, and of course n over 2 is big theta of n. So normally algorithms that traverse linked lists start at the beginning or the end and have to work through the list from there. For our purposes, we actually won't draw head and tail because we typically only draw linked lists to illustrate an algorithm, and it's understood that head and tail are obviously things that you would need, but they just clutter up our diagrams, so we typically don't draw them. Now, since the internal structure of a list it says dynamic, and the idea there is that it's determined only by the status of these arrangements of pointers, which means that if I choose to rewire the pointers locally, then the structure of the sequence that the list describes can change. So right now, this list is encapsulating the sequence 610, 187, -1, -5, 225, and 226. And in an array, if I wanted to get rid of this, I would have to shift a bunch of stuff around. In a linked list, it's sufficient for me to simply detach these pointers and sort of splice the node out of the list. That requires fiddling around with 3 nodes in my list, but the list could have a billion things. I don't have to touch most of them. Now, in exchange for that easy modification, that you could argue that that's the reason you can't do array-style indexing. The structure is so dynamic that it's not possible to know where an element is going to end up. It's not possible to keep track of where nodes are except by following the pointers. Okay, let's try out a couple of these. So I want to, again, insert the value 17 after element 10. It doesn't make much sense to talk about indices because indices are constantly changing, so instead use relative direction. So after element 10. Well, in this case, all I have to do is make somewhere for 17 to live. So I'll make a node for 17. I'll then disconnect these two things, and in a programming course, we'd have to worry about the order where we do this, but we don't have to worry about that here. And then I just tie the node 17 into the list, sort of like this. And now if I traverse the list, 17 indeed is between 10 and 187 in the sequence. And there's a nice typeset version of the same modification. So once I have the node that I want to insert after, or alternatively in a doubly linked list, the node that I want to insert the thing before, I can just splice it in with very, very local operations. All I need to worry about are the new node, its direct successor, and its direct predecessor. That doesn't mean that it's easy to find those things, because I may have to iterate through the list to find the element 10, but once I have it, the modification itself is constant time. And of course, there are often cases in linked lists where you're able to keep pointers to things. You already have a pointer to a particular node for some other reason. And that means if you already have a pointer to the node containing 10, it's constant time to insert an element after or before 10. Now, of course, if I have to search the list, if I want to insert, if I say find the node containing 10 and insert after it, well, that could require linear time because I have to go looking for the node containing 10, and that would, on a unsorted linked list, require linear time. All right, let's try removing something. So delete the element -1 from the list above. And let's just say that we already have a pointer to -1. We know where the node is in the list. Well, then to remove it, all I really have to do is reroute the wiring around that node. So I just make it so that 187 connects directly to -5, and then I've got this node sitting off by itself, and I get rid of it somehow. And in a programming language, there's some way you have to do that. We don't care. We just know that we can rewire the list. And once I have the node to rewire, it's all constant time. It's just adjusting pointers in a fixed radius around the place where I'm making the modification. And so as with insertion, of course, if I have to go looking for the node to delete, then I obviously require up to linear time to do that. Now, because linked lists don't have monolithic storage, not only is it easy to insert stuff, because I can insert by just splicing things in and rewiring, a couple of other operations become really easy, because I can do stuff like merge two sequences together without iterating over, like I don't even have to look at the elements of each sequence to merge two sequences together. If I have two arrays, so here's an array of size, let's do 4, and here's an array of size something larger than 4. If I want to merge these two sequences into one long sequence, then I have to make a big array and copy everything into it, which of course requires big theta of n time, where n is the size of the new array. So it's linear time to make one big sequence out of two small sequences if I use arrays. On the other hand, if I have two linked lists, and this is a case where I would need a doubly linked list, if I have two linked lists and I want to make one big list by attaching one to the other, well, all I need to do is attach the beginning of one list to the end of the other one. And in a doubly linked list, I should have a pointer to both the beginning and end of each list, so I can do it in constant time. I can merge two sequences together with one local modification. I just modify the beginning and end of the two sequences, and I end up with one big sequence. That is a constant time operation. And there are a few times in the course where this becomes sort of useful, the fact that linked lists do have this property. All right, so let's go back to stacks and queues. Stacks and queues, I think, are fundamental data structures. They are as fundamental in the realm of abstract data types as arrays and linked lists are in the realm of ways of storing sequences of data. And I don't think it's a coincidence that arrays and linked lists are the two data structures with which you are the most familiar. They probably were the first two data structures that you learned about back in first year programming. Because, first off, arrays tend to be a fundamental type in pretty much every language. And linked lists tend to be the simplest thing you can build out of collections of nodes when you get to designing your own data structures. It's also worth noting that, actually, I'll spoil something that I'm going to talk about at the end of the lecture, that often things that we view as being lists are actually arrays and vice versa. It's really strange to think about this, but there are ways of implementing a linked list using an array, and strangely the other way around. So normally when we implement stacks and queues, so if in a first-year programming course, if you were told, here's an interface in Java or an abstract class in C++ for a stack, implement the functions or the methods of this interface, then you'd probably use an array or a linked list. And I'm not going to go into how you might do that because, again, that's outside the realm of this course. I will talk about the running times of those things, but beyond that, it's just a matter of first-year programming stuff. And of course, it's true that both arrays and linked lists support tons of operations that the stack doesn't, and that's deliberate. The stack is defined with a very Spartan set of operations to allow lots of flexibility to implement the stack however you want. If the stack had a bunch of other operations, it would be much harder to use any data structure you wanted to implement it. So that's deliberate. We like that. We like defining abstract data types and data structures that have as few operations as needed to get the job done to allow as much flexibility on the back end in terms of how you implement those operations underneath as possible. And so we are going to use stacks and queues all the time in this course. Like they'll just show up randomly in the middle of an analysis or the design of an algorithm. And what I am going to do from this point forward is I'm basically just going to assume that stacks and queues can be implemented with all operations constant. I'm not even going to bother talking about how. I'm not even going to bother saying linked list or array. I'm just going to say stacks and queue. The push operation is constant because it's something that we should accept as common knowledge. And so I'll just go over the running times quickly here. But basically, because push and pop and peek and frankly the enqueue dequeue operations, which are essentially the same things at a different end of the sequence, because all of these things involve inserting at the beginning or end or removing at the beginning or end of a sequence, clearly a linked list can do those all in constant time. If I use an array, it's a little bit different. So if I use an array where I know in advance the maximum size that my stack will ever achieve, keeping in mind that, of course, that size could be an arbitrary number, then once I have created the array, which isn't listed among these running times, once I've created the array, the actual act of adding something to the end or removing it is constant time. I can implement a stack or a queue with an array, a bounded array, where I know I'll never need to resize the array because I've been given a guarantee about how big the array is, what the maximum number of elements in the queue or on the stack is going to be. I can implement all of those operations in constant time. On the other hand, if there's a risk that the number of items added to the stack or a queue is not something I can predict in advance, well then of course there is the chance that I go to push something onto my stack and the array is full, in which case I have to perform a resize operation, and that takes, in the worst case, linear time. Now there's some weird nuance behind this that's outside the scope of our course. It turns out that if we're very clever about our resize operations, we can arrange it so that the amount of resizing that we do overall translates to effectively constant time. We just have to allow for a different analysis technique that allows us to amortize. It's what's called amortized analysis. By using amortized analysis, we can show that if we choose how we resize the array carefully, we can make it so that the cost of resizing the array, if we average it out over all the operations that we do, basically ends up being constant time. That's something we're not going to worry about in this course, but it is worth noting that it turns out that resizable array operations actually are very fast in practice. That the worst case running time, if we're careful, never really causes us much trouble as long as we're willing to amortize it. One thing that we do a lot in this course is work with stacks and queues in other algorithms where we do know in advance how big the stack could be at worst, or how big the queue could be at worst. In those cases, I will assume that we can do the operations in constant time. If anybody wanted to argue with me about the array case, I can always fall back on the linked list case. However, it is worth noting that if I implement those algorithms, I pretty much always use an array to implement a stack or a queue, because I can usually guarantee that I won't need to resize, and arrays in general are very streamlined compared to linked lists. And so because it's often the case that we can bound the size of array we need, usually that is the best option for a stack or a queue. And so in practice, this is what I just said, stacks and queues are implemented using arrays, even in cases where resizing might be needed, because again, with a certain analysis, we can actually reveal that the resize doesn't cost as much as we think it does, as long as we accommodate the cost of the resize over all of the operations. The best I can do as far as that's concerned is to give a brief sketch. And so let's think about this. Here's an array here. It's got 1, 3, 5, 7, and it's got size 4. All right. And now I need to resize it. I want to add more elements to it. So suppose that I double it. Okay, I've doubled the size of the array, and of course, when I doubled it, the array had size 4, and I went to have size 8, and the process of resizing required, let's say, 8 operations. And now I fill up the array, so I've got 9, 11, 13, and 15. Here is my argument. If I take those 8 operations and I argue that each of the new elements that I added, they have to pay their rent. I mean, I just built a house for these 4 new elements, and they have to help pay off the cost of building their house. I'm going to charge each of those elements 2 operations for the cost of building the space that they stayed in. Isn't it true then that the 8 operations that I use to resize the array, if I distribute the cost among each element, after I've performed all 4 insertions, each insertion took constant time? Isn't that true? And the answer, it turns out, is yes. There is a bit of nuance to that analysis. If I'm not careful with that, if I do that sketch with other types of analysis, I could probably prove some pretty dicey things. But the idea behind the amortization that's being referred to here is sort of that. It's if we resize by, let's say, doubling the size of the array, we can argue that before we need to resize again, we have to fill up all of the new positions in the array. And so if we spread the cost of the resize over all of the insertions that we do, we discover that each insertion can sort of cover an equal share of the cost. And that means that the cost ends up actually being constant if we judge by the time it takes to do each insertion. And as a result, it turns out that if you are writing code that needs a resizable sequence in a language of your choice, like C++ or Python or Java, actually let's leave Python out of this. If you're using C++ or Java, you might discover that it turns out even if you have to resize your sequence constantly, using the standard library feature that is a resizable array, so that would be std vector in C++, or array list, so java.util.arraylist in Java, it turns out that these might well be much faster because in general, arrays have very low overhead. Iterating over an array or looking at an index of the array tend to be very fast because iterating over an array requires a simple loop over consecutive locations in memory, versus iterating over a linked list requires walking all over memory using pointers. Because the cost of the resize is really not this much because of that amortization, and we can't prove that, so we have to assume that it's big theta of n. In practice, using array-based sequences tends to be a better idea than using linked lists in many cases. If you tend to do a lot of insertions in the middle of a sequence, that's a different story. So if your insertions are stack and queue-like, if they are push and pop or insert and remove at the beginning and end, often you'll find that these are faster. But if they are modifications, structural modifications to the middle, like insertion and removal in the middle, then yes, that's where you probably would fall back on a linked list. And again, one reason for this is that linked lists, although they are constant time, the constant in question tends to be larger. The number of actual operations needed to do work on linked lists tends to be higher. It's just higher by a constant amount, and so it gets hidden underneath the asymptotic notation. And we'll see in this course quite a few times, especially when the asymptotic notation gives us small numbers like log n or constant, where the impact of specific constants can be significant enough to upset the ordering imposed by asymptotic notation. And that's not a bad thing. That makes sense. As I said at the beginning, our analysis techniques should sort of work downwards from the largest and worst cases to the easiest and cases where, like, constant versus log n and log n, those things can interfere with each other in situations where the constant underneath the asymptotic notation is large. On the other hand, if I look at an n cubed algorithm versus an n to the 4 algorithm, it's relatively rare, although possible, that something that is an algorithm that is formally big theta of n to the 4th might actually be faster in practice than n cubed because there's some huge constant sitting in front of the n cubed that gets masked by the asymptotic notation. One thing that's very interesting that I think helps to prove my point that I'll leave you with is that in Python, so here's some Python code, that looks nice. In Python, you will probably use this data type all the time. And this in Python is called a list. If you put something in square brackets in Python, we call that thing a Python list. And you can iterate over the list, and you can use this append function to add stuff to the end of it. And you think to yourself, yeah, appending to a list is easy because lists support insertion and removal quickly. Because often when you hear the word list, you think of linked lists. And Python calls it a list, so surely this thing has to be a list. Well, no, and don't call me Shirley. It turns out that actually this is an array. In Python, the basic data structure that they call a list internally is implemented with an array. Now, there's a whole ocean of disclaimers I have to give here. So one of them is, well, actually, Python is a language. Python is not a specific implementation of that language. The Python interpreter that you are likely to use, which is called CPython, treats the list data type as an array. And I think that's enough to justify my claim. But yes, theoretically, you could write your own Python interpreter that uses linked lists. However, if you use Python, you've noticed that although Python isn't the fastest thing in the world, there is nothing inherently inefficient or sluggish about Python lists. Even though they're implemented with arrays, they're implemented carefully and cleverly so that they give you all the benefits of a list, and in general, the overhead of operations like resizing the array is hidden underneath the implementation well enough that you don't notice it. If you use Python all the time and you didn't know this until today, then consider the fact that because if you didn't know it, it must mean that it isn't a big deal. You would have noticed that problem by now if it actually were some kind of an issue that affected your use of the language. So keep that in mind. We will often use the fact that a linked list exists as a guaranteed constant time insertion and removal for things like stacks and queues in this course. But then deep down, when we go to implement our algorithms, we'll always use arrays to represent sequences. And that's an example where our formal analysis doesn't map on perfectly to the way we implement stuff, but it still allows us to perform formal analysis. That's the key thing, is we know that linked lists exist. So even if they have a larger constant, we can use them to justify that certain operations are constant time. When it comes time to implement, we can of course make whatever decision results in the fastest implemented code. And that's distinct from algorithm analysis. And those two parts are sometimes at odds with each other, but they generally work together. They work in the same direction. Okay, so there's our discussion of arrays and linked lists. So in case we needed review, there it was. In case there were any special cases that'll come up later, I think I've put them all in this lecture so that we have them. So I've got something to refer you to in case there's questions about it. Now we've got to forge ahead. The next big topic we have to talk about is how to analyze algorithms that involve recursion. That's going to be a big one. It's important, but it's going to be a bit of a journey. And then afterwards, once we get through that tunnel and we see the light at the end of it, we can begin talking about different ways of arranging data, and then talk about how to arrange data in an efficient way. So talk about the study of data structures in more detail.